Alright, so here's the deal. I have extracted this board now. As we know, we're interested in this part approximately. This DC to AC inverter here. And we're going to remove and change electrolytes and these two tantalums here. One of the electrolytes is on the transformer board over here, which I would have to desolder to remove this one, and that will give me opportunity to check the windings if they are in okay shape, and we'll measure the caps and have a look at the condition after we extract them. I have the spares now from Mouser, and it's just to go. I need to clean this gun. So next thing we do is we're gonna pull or recap the display controller board and the PSU. Let me zoom out. We have power supply behind it, quite a zoo of different caps out there. And underneath this one, let me unplug everything back. Like that. I think that will do. Yeah, you can see now there is this, what I assume, display controller board, because it's sharp, the matching vendor to this display itself. And it has also 1, 2, 3, 4, 5, 6, 7, 8, 9 electrolytics of its own. It works fine so far, but all of these caps were sketchy except the tantalums. Both of these were well over 30% capacity, so it means that's probably in poor condition already. This one was dead, the film capacitor was dead, and all in all it doesn't bode well for the remaining caps. I'll just recap so that I don't have to open this instrument suddenly in another few months. So, I recapped the display controller now. I've used new caps which are higher profile than the original ones. This board was probably dimensioned as OEM unit with minimum height, but we don't need it here. It clears pretty decently under the controller board here with plenty of space. So now it's just to hook it back together all and try to power up. Hope nothing pops. Right, so it's alive. As I mentioned, contrast could be better, but there is some greenish backlight and it's clearly legible now. I think we'll go with that. Now I'll put it together and really looking forward to actually test it on some signal. So, while we have this thing split open, let us examine its architecture and design briefly. This is the second board, which I believe is the heart of the system. It has this NEC 8741 microcontroller, which I think is some kind of 8051 clone, maybe with some extended performance. This is the ROM chip with firmware for it. We have a bank of RAM here of 32 kilobyte chips in 6 by 2 384K, substantial amount of memory, static memory for mid-80s. It has been kept with this battery, which is dead, as you know, which leads to it reinitializing completely on every startup. But I have a replacement on the way, this is some sort of, not much UART, but some asynchronous communication chip, which I believe controls this bus, which is two ribbon cables going up and down to different boards. The only other thing here is this DC-DC step-up circuit with AC inverter for display backlight, which we just fixed, and the main relay for it, which closes on power up. So here on the top we have, I think the whole thing is acquisition and signal processing board. So we have probably some kind of attenuator here on the top with precision resistors and relays, and here we have some sort of Schmidt triggers in this fancy silver topped package. There is another chip like that, which is a quad voltage precision comparator. So it also suggests this is sort of analog bit of it around the ADC, which probably hides on some of these chips. Maybe that one, which is socketed. Underneath you have even more of those resistors, kind of hard to see here, even more of those resistors and some relays or optical insulators, I'm not sure which is that. You have this TMS 32OC 10NL, which I think is from the family of DSP signal processing chips with firmware for it, which is probably the thing that runs fast Fourier transform on this board and does the bulk of processing for the CPU. The crystal on it is 16 megahertz, I think. We have another crystal at 10 megahertz as well, so probably runs at around 8 megahertz clock. And that connector is coming from the breakout on common connector for plotter and RS-232, so maybe it has something to do with plotter, I'm not sure. So let's look at the other end. Here we have two extra boards. This one that I've just repaired or recapped has quite a bit of caps. Yeah, I think it was 9 or 10 pieces, and an inductor coil, so it probably has a power component for display. And these two chips are, I'm not sure if there are some serialization drivers, CPLDs or something. You see we have two groups of connectors as well, so maybe for each chip accordingly. That gets connected to the display board, which has 8 plus 6 sharp chips on it, 14 chips. I think they control rows and columns in two groups probably for each of these sharp transceivers on the other end. So these two boards are complete OEMs from Japan. Inside, as you know, is the EL panel that is kinda dead but irreplaceable as of now. This one here is the overall, I think, display controller, because it forwards the signal to the LCD controller board, and also it has CRTC chip, Hitachi CRTC chip, what is called, let me see, HD 46505. I think it's controlling the CRT via this, what has to be one wire, I guess, composite output. That could be plan B if I couldn't recover the display. So yeah, all in all we have 1, 2, 3, 4, 5 boards with quite high component counts. All of them use static RAM throughout. This one has its own RAM buffer, also in its 32 kilobyte SRAM chip. So They could have spared with DRAM a bit probably in some places here, but didn't bother. So now it's just to assemble this whole thing back, and we're good to go. Can use the instrument and maybe try some actual signal capture with it. Right, so this is about as good as I could get this display. As I say, the EL panel is on its last legs anyway, and there is no replacement to source anywhere. And this is the maximum on the contrast knob of the device. So a pretty stark contrast to a modern function generator screen, but we have what we have. So let me turn the 10 kHz sine, let us take 5 kHz sine on output 1. We have a menu: instant spectrum, instant time, average spectrum, average time. Let us try instant spectrum. Yeah, the output is disabled, of course. Out of band. So then we need to use this button to select a horizontal range, I guess. Range increment 5. Yeah, we see, I guess, some harmonics. So we have memory. We can store different captures. Panel store. It's probably some settings storage. There is user manual actually available for it, but I haven't got as much as to read it. View average time. Free run. 1 volt peak to peak, 10 kHz. Well, that's neither here nor here. 10 kHz is range. 1 volt peak to peak is the signal we get. And cursors. Yeah, we can actually move the cursor. You see that faint dashed line. But it shows smack on 5 kHz. If I put a square signal at 5 kHz, let me see. Yeah, quite a bit more harmonics as expected. But drop back to pulse. Pulse of 10. Let us reduce it a bit. Pulse at 5. That's quite tidy. We can generate some noise, which looks like noise, fair enough. Type. Let us use a pseudo-random sequence, for example. Oh, have you seen that? This is PN11. We can have as long as PN23 here. Well, pseudo-random it looks. It looks like the part. Bitrate 10 megabit. That's quite a lot. 1. No. Kilobyte per second. Right. 5 kilobyte per second. Kilobit, of course, sorry. Yeah, I have no idea how the audio spectrum of pseudo-random binary sequence should look like, but apparently like that. It also has average spectrum or instant time domain signal, which looks a bit like, yeah, fair enough, these are pulses. If we switch to sine, we get, well, sine horizontal, we can probably increase range to make it a bit right maxed out. Let me squash it a bit vertically maybe. Sensitivity increase, sensitivity decrease, gain up, gain down, gain down. Sensitivity decrease. Yeah, right. Alright. That's look like a sine wave. Would you say that? I would say that. So it appears to be working. Most of the functions at least. What do we have under trig? Free run, single trigger. That's trigger, of course. We don't have any trigger attached here. But that's an interesting, good feature to have. Instant time. Average time. Average spectrum. Yeah, you see it has an option for battery charge here, which means it's only missing a battery in the cable probably from that charger circuit to operate portably. Not that I want it. I don't think we have two other FFTs, one in the scope we have and another portable audio measurement device slash spectrum analyzer. So this probably gonna be used on my further experiments with pseudo-random sequences. We're getting 5 kHz here, probably because I decreased the sensitivity. Yeah, if I increase sensitivity it brings out the harmonics. But the instrument works, I would say. It's maybe not so impressive by today's standards, but we are very much in audio lab here doing lots of stuff with sound, so we'll always find a use for this instrument and maybe do some direct microphone pickup with it. Huge advantage of it is it's completely silent. All the noise was coming from this pulse ARP generator, but the instrument doesn't have any fans, as you've seen. Really helps when you're working with microphones. So I hope you liked this repair. A bit slow and bumbling on my part, but remember I'm more of a software than a hardware guy. This is kind of a side gig for me, repairing old broken stuff. So I hope you enjoyed the videos. See you next time.